Hello everyone, welcome to today's class. This is Teacher Simon taking you through Cambridge International AS and A-Level Chemistry for February-March 2024, paper 2-2. Question number 1. Bismuth is an element in group 15 of the periodic table. Part A. Bismuth has metallic bonding. Draw a label diagram to show the metallic bonding in bismuth. Now in metallic bonding, we see the attraction between the positive metal ions, okay, and the delocalized electrons. And these positive metal ions are in a regular pattern. The ions are in layers that can actually slide over each other. Okay, so we can draw something like that. Then we put the plus, implying that these are positive metal ions, the bismuth ions. And then in between them, we can put electrons, these delocalized electrons, which are actually negatively charged. So any bonding is an attraction between two things, okay? It is an electrostatic attraction between the positively charged metal ions and the delocalized electrons. So here I will say this is bismuth ions, or I can just say metal ions. And then this one, these are delocalized electrons. They are not just electrons, but delocalized. To be local is to stay in one place, you see. Now delocalized, that means you are not in the same place, you are moving about, so they are free to move everywhere. So that is that. Then part B, bismuth reduces water to form bismuth oxide. A colorless gas that ignites with a squeaky pulp forms. This is hydrogen. That is hydrogen gas. Then they are saying construct an equation for the reduction of water by bismuth. So I'll write bismuth here, then plus water. And remember, an equation is not correct unless it is balanced. So we shall have bismuth oxide, then plus this gas here, which gives a squeaky pulp. Then we can balance. You can see that these are two bismuth atoms. So this way we shall add a 2. And then when we try to look at what is here, oxygen, these are 3. Okay. If oxygens, these are 3, that means I will put a 3 here to balance the oxygen here. And then hydrogen becomes 6. So I'll put a 3 here to also make hydrogen 6. So that would be the equation. Now, you don't need to put the states, okay? You don't need to put the states unless they tell you to include the state symbols. That is when you do so. So just leave it like that. Now, this oxide here is a yellow insoluble solid that melts at 1090 kelvins. The molten compound conducts electricity. So if the molten compound conducts electricity, then that means it's an ionic compound, right? Now they are saying deduce the structure and the bonding of bismuth oxide. Explain your answer. So the structure is either giant or simple, but this one is going to be giant. Why giant? Because of the high melting point. So giant structure. Then we say because of high melting point. And then the bonding is ionic, like I said before, ionic bonding, because it conducts electricity, in molten form. So that is that. Then part C, Bismuth oxide can be used to form sodium bismuthate, as shown in equation 1. This is the one here. Deduce the oxidation number of bismuth in bismuth oxide and sodium bismuthate. Oxidation number of bismuth in this one is which one, and also here. Now let's see what is happening here. I'm going to look at this one here. I don't know the oxidation number of bismuth. Let's say it is N. So since there are 2, I'll put 2N. And then oxygens are 3 of them, but the oxidation number of oxygen is a -2. Then this one will be equal to 0 because no overall charge. So meaning N is going to be equal to, this is -6. So when it crosses, it becomes a +6. And then we divide by 2. So this one is going to be +3. So that means here we'll put +3. And then for this one here, for sodium, remember sodium is in group 1, so it loses 1 electron, then it becomes positively charged, so that is a 1. Then for bismuth, I don't know. And then for oxygen, there are 3 of them, and each of them is having an oxidation number of -2, so this one is equal to 0. Then N is going to be, this one is -6 plus 1, that one will give us -5. When it crosses, this one becomes a +5. So that means the answer I'm going to have here is +5. Then Roman 2, identify the reducing agent in equation 1. The reducing agent is the one that gets oxidized, okay? It is the one that loses electrons. It gives out electrons, and then what receives those electrons, it is reduced. You get it? So this one being a reducing agent, that means it has what reduces another. As simple as that. So when you look at the oxidation number here is a +3 in here, and the oxidation number of bismuth here is a 5. So meaning there is increase in oxidation state. So if there is increase in oxidation state, a reducing agent gets oxidized in return. So the oxidation number of bismuth in here has increased. So that means this one here is the reducing agent because it has gotten oxidized. So I'll write bismuth oxide here. That is the reducing agent. Maybe to write something small here, I will say a reducing agent. A reducing agent gets oxidized. Gets oxidized. In other words, the oxidation number increases. Its oxidation number increases. Okay? And you can see that the oxidation number of this one has increased to this one here. Part D, sodium bismuthate is an oxidizing agent with similar properties to potassium permanganate. Then figure 1.1 shows an example of the use of sodium bismuthate as an oxidizing agent. Now, we are seeing this one is a diol, but then under sodium bismuthate, we are seeing a ketone. That means we are seeing this one broken down, and then this one is an aldehyde. Okay. Explain the term oxidizing agent. We have been talking about it. So this is a substance. You don't say it is a compound because we can have elements. And you know a compound is a group of elements. We can have just one element. So a substance that removes electrons from another. That removes electrons from another. Remember, an oxidizing agent, for which it gets reduced. Or I can actually say gains electrons from another. Gains electrons from another. Many ways of writing this. Then Roman 2, compound X forms when methyl but2-ene reacts with potassium permanganate. State the essential conditions of this reaction. Now we can see that this is a diol. If it's a diol, methylbutadiene is this one here, CH3, CH, then double bond, then C, then we have a CH3 here, and then the CH3 here. So we are seeing an OH here, and then an OH here. So automatically this one has to be acidified. The potassium permanganate has to be acidified, cold, and dilute. Okay, so I just put acidified, okay, cold, and dilute. If it is hot, acidified, and concentrated, then we break everything here and then we oxidize this carbon here. Then we get we shall get a carboxylic acid here and also a ketone there. So for this case, for formation of a diol, this one must be cold, acidified, and dilute. Then complete table 1.1 to show what is observed when compounds Y and Z react separately with the named reagents. Then the first one here, this is sodium carbonate. They are saying with Y, no reaction. Observation with Z. Let's look at Z. Sodium carbonate, first of all, will react with an acid. Okay? Reacts with acids. Okay? Reacts with acids. So this one is not an acid. It is an aldehyde here. So that means no reaction. So we shall say no reaction. And then the second one, alkaline iodine. Now for alkaline iodine, we must have these groups here. The CH3, CH, then OH. This group must be there for alcohols. Okay? And then for ketones, we must have, or carbonyl compounds, we must have a CH3, then CO. Okay? This is for carbonyls. Majorly for ketones. But we can also have methanol. Okay? I mean ethanol, sorry. Ethanol, even this one can give a positive test because it has the group here. But usually many of them are ketones. Now, after this, these ones here, this group and this one here, if they are available in those compounds, then we shall get a positive test. Okay? This is actually what we call iodoform test. Iodoform test. We get a yellow precipitate, and that precipitate is the triiodomethane. Now, let's look at Y here. Y has gotten a CH3 here, a CH3 here, and then there is a carbon here. So, of course, there is CH3CO. Which group I've talked about here? You see that? So, that simply implies that Y gives a positive test. And also Z will give, because this is CH3 here, then CO. Just like I said that ethanol gives the positive test. So we shall see a yellow precipitate. Yellow precipitate. It is the same thing that is going to be here with Z. So I'll just put the same, as simple as that. Then we go to the next. This is 2,4-dinitrophenylhydrazine. This one gives a positive test. The positive test here is seen for carbonyl compounds. So Y is a ketone. This one is an aldehyde. So they both give a positive test, which is actually an orange precipitate. Orange precipitate. So the same is what I'm going to put here. As simple as that. Then TOLLEN'S reagent. TOLLEN'S reagent, this one gives a positive test with aldehydes, not ketones. So we shall see a positive test with this one here, but not with Y, because Y is a ketone. So Y, we shall put no reaction. And then there is a positive test for Z, which is an aldehyde, which is actually silver mirror. As simple as that. Then Roman 4, construct an equation for the reaction of Z with sodium hydrodoborate. Use H to represent an atom of hydrogen from the reducing agent. Now, we shall get Z is CH3, CHO. It's an aldehyde, ethanol, then plus. For a reducing agent, you are going to reduce the aldehyde to a primary alcohol. So we shall get CH3, CH2, OH. So how many hydrogens have been added here? This is 3, then 5, 6. So altogether, those are 6 hydrogens, right? But then here there are 4 hydrogens. That means 2 hydrogens have been added. So I'll put a 2 here. That will be the balanced equation. Part E, sodium bismuthate can be used to determine the concentration of manganese 2 ions. The ionic equation for the reaction is shown in equation 2, which is this one here. A student uses the following procedure in an experiment. Add 100 cubic centimeters of a saturated solution of manganese 2 to a volumetric flask. Add distilled water to the flask to make 1 liter distilled solution. Diluted solution. Titrate 25 cubic centimeters of the sample of the diluted solution with 1 molar sodium bismuthate. The 25 cubic centimeter sample of the dilute solution of manganese 2 reacts completely with exactly 21.5 cubic centimeters of 0.1 molar sodium bismuthate. Then calculate the concentrations in moles per liter of manganese 2 ions in the circulated solution. Show your working. Now, for such questions, we begin with the standard solution. A standard solution is the one that has gotten the known concentration. Okay, so we need to find the moles of sodium bismuthate, because for it we know its volume and then the molarity here. So sodium bismuthate, the moles we are going to have, this is 21.50, which has to be in a liter. So out of 1,000, then times the 0.1 here. Okay. Why do we do this? This one is like saying, you just begin with this statement here. This one alone means that 1,000 cubic centimeters of solution, contains 0.1 moles of sodium bismuthate. That's what it means. Okay, then how about the 25 cubic centimeters? 21.5 cubic centimeters. So this one will contain, then you say 21.5, then times the 0.1 here, and then you divide by 1,000. You see the same thing here? So what we need to do is to just get that volume given to us, and then you just divide it by 1,000 and then times the molarity which is given there. As simple as that. Then you will be in position to get the moles. Now, what do we get here? 21.50 times 0.1, then all of it together out of 1,000. That one gives us 2.15 times 10 to power negative 3. 2.15 times 10 to power negative 3. Okay. Now, after getting the moles of sodium bismuthate, then we can go here and we find the moles of this one here, manganese 2, which reacted. Okay. So from the stoichiometric equation, this one is clear. It shows that 5 moles of sodium bismuthate Now, sodium bismuthate is soluble in water. Okay, so when we say the bismuthate ions here, you should know that it is the whole thing here. Okay, then sodium bismuthate here, the 5 moles of it react with the 2 moles here. Okay, react. Let me use first principles for you to understand this very well. So react with 2 moles of manganese 2 ions. Okay, then how about the 2.15 times 10 to power negative 3? How about these moles here of this bismuthate will react with, then we say this one here times this, then divide by 5. 2.15 times 10 to power negative 3, then times 2, then you divide by 5. In other words, just get this times 2 over 5. Okay, then what do we get here? So the answer we have here, we shall multiply it by 2 out of 5. And then we get 8.6 times 10 to power negative 4. 8.6 times 10 to power negative 4. These are moles of manganese 2 ions. Okay. Now, these are the moles of manganese 2 which reacted. But they are reacting from which sample? They said the 25 cubic centimeter sample of the diluted solution of manganese 2 now completely reacts with this. So that means these moles are now contained in the 25 cubic centimeters, okay, of the diluted sample. So we shall say that 25 cubic centimeters of solution, okay, of actually the diluted solution of the diluted, because remember there is saturated solution of the diluted solution it contains this 8.6 times 10 to power negative 4 moles of manganese 2 ions. Then how about 1000 cubic centimeters of the diluted solution will contain, and we have 1000 here times the 8.6 times 10 to power negative 4, then we divide by 25. It's like getting this 25, it goes here how many times? 25 goes into 100 4 times. So it's like getting this answer here times 40. The answer we have here, we are going to multiply it by 40. Just say times 40. And then that is 0.0344. 0.0344. Okay, these are moles per liter. Okay, moles per liter. Now, for the saturated solution, because what they have told us to find, it is for the saturated, this is for the diluted. So we shall say for the saturated solution, that is 1000 cubic centimeters. I mean 100 cubic centimeters, moles of manganese 2 here shall be equivalent to, you get this 0.0344, then multiply it by 10, because in 1000 you are having 10 hundreds altogether. So in the saturated one, in other words, they got that concentration which is in 100, And then they added all of them together, 10 of them. In other words, I'm going to use what we call, this is inverse proportionality. In mathematics, we talk about inverse proportionality. It's like when you're having very many people, if you have very many people to do a certain job, it is going to take a shorter time, not so? But if you have very few people to do the same job, it is going to take longer time. Now, the concentration, every time you are adding, let's say water, you are diluting, the concentration reduces. Now, the saturated solution, that means you will need little water to add to that mass that you are putting there. Okay? At first, you are using 100 cubic centimeters, but then you diluted to this mark here, to 1 liter, to 1,000. So, how many cubic centimeters, how many of these 100 are in a liter? It is 10 of them. So that means just get this one here and multiply it by 10. And then your answer will be 0.344.